1999. Let's see what that is. Again, have a calculator handy. 3,645. Again, that would be the 7th term in that sequence. Moving on to the next problem. In this problem, we have the population of Florida from 1990 through 1997 is shown in the following table. 90, population in millions, 12.94 million, 13.2 million, 1992, 13.46 million. Okay, so we have Florida's population here from the 90s. And let's see, show that the population is increasing geometrically. So just, I don't know where this might be hard to figure out, but if you think about it, right, with some guidance here, if you think about it, a geometric sequence, right, show that it's increasing geometrically. If this were increasing geometrically, then I'd multiply this by a number, and whatever I got, I'd multiply this by the same number, right? So I'd keep multiplying by the same number to get each of these next numbers, right? To get each consecutive value, I'd always be multiplying by the same number if it was increasing geometrically. So what I'm getting at is, if I just divide in reverse order, I can show that this is increasing geometrically. So again, for this one, our approach is to divide in reverse order. And so again, if you divide in reverse order, right, you're going to divide 14.86, you're going to divide that by 14.57, and then 14.57 you'll divide by 14.28. And I would do this, I would just test this out on a calculator, and I'd go down the whole list dividing these terms, right, these terms in reverse order. So again, when I get down to here, I would divide 13.46 divided by 13.2, and on this last one, 13.2 divided by 12.94, and I do all that on a calculator, guys. So I already did that, and each of these, when I divided 14.86 by 14.57, it rounded to 1.02, and some of them were, not identical for every decimal, but they all rounded. When I divided backwards, they all rounded to 1.02. So point is, by dividing in reverse order, I was able to see the exact same ratio pop up over and over again. 1.02. So that's how I'm showing that this is increasing geometrically. So ratio R, right, I have a constant ratio, or a common ratio, is common, so it's geometric, right? If I can show that common ratio of increase or decrease, it's geometric, okay? They want me to write an equation for the geometric sequence describing population growth for Florida n years after 1989. Well, remember, your formula is, if you can check back up at the top too, it's a sub n equals a sub 1 times r to the n minus 1 power. So if I'm using that formula to write a rule here, it's not asking me for any term, so a sub n will stay the same. But a sub 1, remember, it's the first term would be the next year after 1989, so the first term would be your 1990 number, 12.94. And then you have r, which we established is 1.02, so times 1.02 to the power n minus 1, okay? And then they want me to estimate Florida's population in millions for the year 2013 and check for accuracy. So remember, in 2013 it'll be this many years. Let's see, n will be it's 1989. Oops. So n will be 2013 minus 1989, right? So you can punch that in. Should get 24 years for n, right? So I'm going to plug that in. I'm going to plug in n is 24 into my original equation here, or my previous equation, that is. A sub 24 equals 12.94 to the 1.02 times, again, n minus 1, so 24 minus 1, that's going to be 23. We'll use a calculator for that one. Definitely use a calculator for that. So 1.02 to the 23rd power, that's just 1.02. Raise it to a power with this little arrow key. At least on this calculator, that's what it is. 1.02 to the 23rd power. And there we are. It's 1.5769. I'm going to round that. 1.5769. And now I'm going to multiply that by 12.94. And I got 20.4. So in this problem, we're basically saying that the population in Florida in 2013 will be 20.4 million people. If you were to look up Florida's population in 2013, if you're able to find that information, it should pop up around 19 point some million. So this estimate's pretty close. Our chart's not bad, but it wasn't exactly accurate. So I would just say it's close, but not exactly accurate. Last one here, write the general term for the geometric sequence 3, 6, 12, 24, 48. You guys can figure out quite a few things from here. You can figure out that the first term is 3, right? A sub 1 is 3. You can also look at this and see what they're multiplying by, right? Let's see, 3 times 2 would be 6, 6 times 2 is 12, 12 times 2 is 24, and 24 times 2 is 48. So pretty simple to figure out what they're multiplying by, which aka would give me the r equals 2. And I could now take that, remember the general term here, it says write the general term. That just means write the equation as stated in this problem. So if you take the original equation, right, a sub n equals a sub 1 times r to the n minus 1 power, you can plug in a few things here, right? You don't have n for example 7, but you have a sub 1, that's 3, times r, that's 2, to the power n minus 1. So that's the equation for that sequence. And use the formula for the general term. So I'm going to use this, right? I'm going to use this to find the 8th term. So now I have n equals 8 as my guidance. So my 8th term, 3 times 2 to the, remember 8 minus 1, that's 7. 2 to the 7th power is going to be 128, and then 3 times 128, let's just use a calculator for that one, make sure we get it right, 384. So the 7th term for this sequence would be 300.